picture of this thing. Okay. Probably good if you put in an axis coordinates to think about. Plus, again, the visualization is aided by that. Right up through. Seeing that? I guess you're low enough that you're probably seeing up in here, right? Well, we want to draw sort of a typical slice. You know, I have slices all the way through this object, but you know, at some height, you know, that's sort of a typical representative piece. You know, I've got then a circular disc that sits in here and has some center. You want to make the marking of the center look right. Make sure you put the one mark in the same direction as the x-axis, the other in the same direction as the y. You cross it. That'll make it look like it's in the same direction as the plane down here. Same kind of surface. Well, what are we trying to do? We're trying to set up a way to add up a whole bunch of little volumes based on this object that fill from here to here. So if I examine this thing, just kind of say to myself, what's the basic, you know, volume of this? Well, what in general, if this had a height and a radius r, you'd say that the volume is some pi r squared h. You'll notice that that's like an a of x dx kind of thing, or really, I guess, a of z. This is like that a of z, and this is like a dz. Remember the initial discussion I had? An area times a perpendicular will give you a volume. And so what? I need to set this up so that, you know, from the bottom here to the top I can have expressions for these in general. So, well, actually I'm already identifying what the dz is like the h. So this is going to end up being an integral with a dz in it. Right, and the a of z term I know is built out of this kind of pi r squared structure, so certainly pi wouldn't change. The issue is, what is r? Well, r has to be what? Described in terms of z, because z is the variable that we're working with. So we have to answer the question, you know, for a given value of z, how big is r? You know, for this value of z, how big is r? For, you know, that value of z, how big is r? We're going to have an equation that gives us that relationship. You know, looking at it here is probably not the easiest way to get that relationship, but if I say look down the x-axis at it and picture this more flattened out, I'm dealing basically with that, right, where this is the r value that I'm wondering. Right? I know, you know, this full height is up to h. What else do I know? I know that, you know, if I'm going to talk about being at a height, I'm going to call it, what, the value z that I'm at, because I'm on the z-axis. What am I trying to do? I'm trying to write r in terms of z. Right? That's the game here. So I have a dz integral. Right now I just have it as a general notion r. What? Similar triangles would probably work in here if I looked at with this little triangle here to this taller triangle. But in order to do that, right, I also need to know this distance in here. What, if that's h and that's z, then this is h minus z. And now we should be able to go for it. Right? So with similar triangles, what am I trying to do? I'm also trying to convert r to z. Right? So if I'm going to convert r to z, it's best to start your similar triangles and saying then r is to something out of whatever is to whatever. So what r would be on the little triangle is then to say the height of the little triangle. So h less z is like what? This value, what was that value?
R.
Yeah, that's the big R, right? The one that I decided to call the radius of that cone, right? So that's the big R. So as big R is to, well, yeah, this distance in here is the big H, right? It's the height. So there it is. And so what? That's going to say that I can replace R's with big R over big H times H less Z. Therefore what? Instead of this R squared, I have this thing squared. So I have R squared over H squared, H less Z squared. That's R squared. It's kind of a typical game that we play. You know, you see it in sort of generic form, and then you ask, how can I get it into the variable that we're integrating with respect to? Often a similar triangle and these sorts of little tricks make a difference. You guys seeing it okay in the back? Want me to keep it up higher, or does it need to be written bigger?
A little bigger, please.
Okay. All right. All right, so anyhow, are you okay up to this point here?
Yeah.
All right, so so I can say what we have a pi big R squared over big. I'm not writing it bigger, am I? Zoom in. Pi big R squared over big H squared. Integral, I guess I didn't note it here, but what, the slices are a z value of 0 up through a z value of h. Right, so put in 0 to big H here, 0 to big H here. So I took all that out, so what's left inside is just my h less z squared dz. All right, so well, you could use an inverse chain rule if you want. Just make sure you catch that negative. Just get that h minus z cubed over 3. Or you could run through the following u substitution. Right, let u be the h less z. Right, du is going to be what? That's a constant, so that goes to 0. So minus dz. I don't have a minus in here, so I'll put the minus on the du and call it dz. Alright, so let's see, we then have pi r squared over h squared, integral, that's what I call u, so that's u squared, dc, I get an extra negative with the du. What, I can change the limits of integration, that's something we haven't practiced much, but should. Well, when I read this, I see z is 0 and z is h, and I need the corresponding values here, and what? This is the thing that tells you how to convert, basically, because that's the relationship between u and z. So if z is 0, just put 0 in there, and obviously then u is h, so lower limit then gives me an h there. And what, if z is h, well, if you put an h in there, you get h minus h, which is 0, so u must be 0. So instead of from 0 to h, we go from h to 0. That's not always the case, right? The flip-flop is just not a coincidence here, it's just because of the structure of this thing, basically. Anyhow, right, we know how to get a cube over 3 right out of the integral. Right, so we'd have what, negative pi r squared over h squared. Right, getting our u cubed over 3 from h to 0. Now, depending on how you like to do this, some folks don't even bother with the limits here. They just go back to writing in terms of z, which you can do. In other words, you can look at this and say, all right, I have a minus pi over 3r squared over h squared, taking 3 out. And what? Then you have u, which is the h minus z, right, cubed. And then you'd have to write it in the old evaluation, right, from 0 to h, that way, right? Or, right, you'd what? Just leave it in this way and say that you have a minus pi over 3r squared over h squared with what? U cubed from h to 0. Just want to make sure you see the parallel here. If I evaluate this one at h, right, first term is 0 cubed, so we get just this constant out front again. And I have what, a 0 cubed minus, and then when you put in 0 in here, right, you get an h cubed. If you go with this form, instead of bothering with going back to z, as long as you did this part correct, right, your answer to this is going to be identical to that. You have this minus pi over 3 r squared over h squared with, and when you put in 0, you get 0 cubed. When you put in h, you get h cubed. So, obviously, these things are the same. And so, you do one or the other. You either go back to z and substitute, or be happy with your new limits and keep it in u. Either way, well, we got a double negative, so it's positive. We got some cancellations with h's. And you have then a third pi r squared h. That's probably familiar to most of you. The volume of the phone.